Hello, my name is Nguyen. This is my presentation for DATA670 on my project for dementia risk prediction in patients based on behavioral, lifestyle, and demographic factors. Now, to review my project, uh, using two sets of publicly available data, the goal of this project is to identify trends in behavioral habits, demographic features, and lifestyle choices that show a strong correlation with a positive or negative diagnosis. Dementia refers to the degeneration of nerve cells in the brain, which affects memory, behavior, and the capability to perform everyday tasks. Dementia affects over 55 million Americans worldwide, with nearly 10 million new cases each year. As the baby boomer population of America ages over the next few decades, it's expected to affect 12 million Americans by 2040. My analytical problem that I'm analyzing in this project is whether we can detect patients at greater risk for developing dementia based on behavioral, demographic, or lifestyle characteristics, and if possible, can we develop a predictive model capable of identifying patients with a higher risk to facilitate early detection without access to medical imaging or prior testing. Unless a patient already suspects they have symptoms or have gotten an MRI scan done, they are unlikely to suspect that they were at risk for dementia. If we could determine patients who are at risk and encourage them to be more aware and regularly test for dementia, we could provide early detection, which could increase the effectiveness of interventions, either with medications that would be more effective during the early stages to control for the symptoms, or by changing behavior to reduce risk. Then, develop a model that can accurately predict patients who have a greater risk for developing dementia based on features that can be gathered without the use of prior tests or medical imaging to preemptively screen patients and encourage regular testing for signs or symptoms of dementia. Now, to review, I'm using two different sets of patient data sourced from Kaggle. The first dataset includes 2,149 records with 35 variables in the first dataset. The second dataset includes 1,000 records with 24 variables. During the data preparation stage, the datasets were checked for missing data and found to be fully intact. The variables that were identifiers or had no scale or context for their recording were removed. Measurements such as vitals that were only relevant at the time of the data's recording were also removed. Along with the modification of some variables to make them consistent between the datasets, the variable risk scale was added. This would be a simplistic calculation that tallied risk factors for dementia such as smoking, certain age ranges, or a history of specific pre-existing conditions to determine if a scale could be used to quickly assess a patient's risk for dementia through their medical history. With the inclusion of this new variable, the combined dataset includes 17 variables with 3,149 total records. For the analysis, this was done through association rules mining on both datasets separately. So the figures shown in this slide are the association rules found for dataset 1. These rules were filtered down to rules that had a right-hand rule of either dementia equals yes or dementia equals no. In the first dataset, no rules were found for a positive diagnosis of dementia. However, the rules mining identified 6 rules with statistically significant rules lift greater than 1 that were correlated with a negative diagnosis. These rules pointed out that patients with a high activities of daily living score and a negative history for head injuries, memory complaints, and behavioral problems were strongly correlated with a negative diagnosis. While this was expected, 2 of the 6 rules also include patients who were ethnically African American were also highly correlated with a negative diagnosis. The second dataset came up with many rules, so I focused on the top 20 rules found. The association rules mining for this dataset found a few rules with a correlation to a positive diagnosis, generally based on cognitive test scores. So, patients that scored an 8 or below on the 0 to 10 scale, or patients with depression, were highly correlated with a dementia diagnosis, as the top 6 rules sorted by rules left. Now, these rules were within my original expectations, since dementia and decreased cognitive test scores would be classic signs of dementia onset. The following rules were often combinations of features with statistically significant correlations to a negative diagnosis. Something noticeable was that these rules often included hand dominance, gender, or patients who either never smoked or were ex-smokers having similar correlations with a negative diagnosis for dementia? In terms of gender, it was female patients. In terms of hand dominance, it was left-handedness. Other features that were strongly correlated with a negative diagnosis were the lack of an APOE4 gene, which is commonly seen in Alzheimer's disease patients, as well as a lack of hypertension and depression, which are common symptoms of dementia. Looking at the association rules, there were many rules identified for patients that did not have dementia, but very few that had a strong correlation with patients that were diagnosed with dementia. Uh, this is likely due to a class imbalance in the target variable, as there was an approximate 60-40 ratio for patients not diagnosed with dementia to patients that were, as well as a relatively small sample size due to the lack of data sets with patient health information compliant with privacy laws that were publicly available for this analysis. Along with the association rules mining, the significance of each variable in predicting the target variable dementia was tested with a chi-square test, shown in the slide through the histogram on the top right. The influence of depression and diabetes was expected based on known risk factors. However, the graph provided through SAS Enterprise Miner also included smoking, sleep quality, physical activity, and gender as significant predictors of dementia. Though only sleep quality was statistically significant, gender, physical activity, and cardiovascular disease were still variables considered significant enough to include in the visualization despite the inability to reject the null hypothesis for these three variables. Now, looking at the variable risk score, which was added as a potential measurement to predict dementia risk in patients, the scores had similar distributions in both classes of the dementia variable. The median and mean were both similar for patients with and without dementia, with a slightly wider range in non-dementia patients. The distribution of scores for patients with dementia was slightly tighter, but the similar clustering in the center means that the use of a risk scale, at least with the simple calculations used here, does not provide a clear enough distinction between patients with a high risk versus patients with a low risk of developing dementia. However, since the calculations were made based on known risk factors, the variables contributing to a positive diagnosis must apply differently for each variable, meaning weights would need to be determined to accurately calculate a predictive scale. Based on how the association rules and chi-square plot describe the significance of certain variables in combination with the finding of the risk score variable, I conclude that there is no easily discernible direct relationship between the variables and a positive dementia diagnosis, and that dementia is a multifactorial disease with a nonlinear relationship between the variables and dementia prediction. This conclusion led to my choice of models for this project, which were a logistic regression model, a decision tree model, and two ensemble models through the use of the random forest and gradient boosting algorithms. These models were chosen to reduce the risk of overfitting, in addition to reducing the effect that class imbalance in the target variable may have on each model. This was also addressed by the use of oversampling to increase the representation of the positive class in the target variable dementia. The logistic regression model was included as a baseline model since it's easy to train and implement. However, it assumes a linear relationship between the variables while also being sensitive to outliers and class imbalance, so this model was expected to perform the worst of the four. Here is a visualization of the model's classifications and the classification matrix of the training and validation partitions. In terms of metrics to determine model performance, the focus will be on the area under the curve score, or AUC score, the false negative rate, and the sensitivity and specificity of each model. Looking at the logistic regression model, the AUC is acceptable at 0.826, which is a very good performance. The false negative rate is too high at 34% approximately, and the true positive rate is too low at 0.656. So the model performs poorly at being able to classify true positives from false positives. Next, we have the decision tree model, which was chosen because it's easy to interpret and capable of handling nonlinear relationships. They are also robust to outliers and irrelevant features thanks to splitting. However, decision tree models are susceptible to overfitting with smaller datasets, and imbalanced classes in the target variable can introduce bias, which can become amplified through splitting, making the model less sensitive to the minority class. Here's the classification chart for the decision tree model as well as the classification matrix. The decision tree had the lowest false negative rate. However, it also reported the highest false positive rate. The model had a good specificity and sensitivity, meaning the model is strong in accurately determining a positive and negative classification. However, it had a very low area under the curve compared to the other models. Finally, we have the ensemble models. So there were two ensemble models used in this analysis. That is the random forest and the gradient boosting models. Random forests use bagging to create a number of decision trees in parallel, then aggregate the results by voting. These models tend to be robust to outliers and noisy data, and if necessary, they can handle datasets with missing data. Random forest models also include their own cross-validation by partitioning a specific subset of the decision trees made into an out-of-bag partition that can be compared with the results of the aggregate model. They tend to be faster in model development thanks to parallelization, but they can also become computationally expensive and are unsuitable for real-time predictions. Gradient boosting models improve prediction accuracy through iterations, adaptively applying weights to focus the model to train on weak learners to better distinguish the classifications. They are, however, sensitive to noisy data, which can lead to overfitting or the model underperforming. They are also computationally expensive, and because of the nature of the algorithm, it's much harder to follow how the algorithm reaches the results that it did. This slide includes visualizations and the classification matrix for the random forest model, while this slide shows visualizations and the classification matrix for the gradient boosting model instead. The random forest model shows the highest area under the curve score at 0.873, while the gradient boosting model shows the next highest area under the curve score at 0.856. The random forest model has the second lowest false negative rate at 0.164, but also the second highest false positive rate at 0.264. This likely affected the precision due to the large number of false positives as well as relatively large number of false negatives. By comparison, the gradient boosting model has a relatively good low false negative rate at 0.18 and a relatively low false positive rate at 0.228, as well as a relatively high classification accuracy at 0.79 or 79%, as well as strong sensitivity, specificity, and precision compared to most of the other models. So the ensemble models are very strong contenders for the optimal model of the four observed. Comparing these statistics side by side for each model, we can see that the random forest model has the highest area under the curve score as well as the strongest ability to distinguish positive cases. The decision tree shows the highest specificity, so it has the strongest ability to distinguish negative cases, while also maintaining the lowest number of false negatives among the four models. The logistic regression model has the lowest false positive rate, however, it pales in comparison to every other model. The purpose of this project is to produce a screening tool capable of identifying patients with an increased risk of dementia, advising the patient to conduct regular screenings to ensure early detection of any symptoms. Therefore, in terms of priority for metrics to determine which model is the most optimal choice as a diagnostic tool, we have to consider the area under the curve, followed by the false negative rate, the sensitivity, and the false positive rate of each model. In the context of this project, a false positive would have relatively weak consequences, where a patient is screened, tested, and likely not diagnosed with dementia. However, a false negative could lead to a patient missing the ideal time for early detection, at which point interventions and medications could become less effective for their treatment. Using these metrics, this narrows down the choices between the random forest model and the decision tree model. The decision tree model has the lowest false negative rate, but the random forest model maintains both a low false negative rate as well as a greater specificity, greater area under the curve value, and greater classification accuracy by comparison. Therefore, I can conclude that the random forest ensemble model is the champion model of the 4 observed models in this project. Now, looking at the KPI set before this project started, first KPI was, can we identify statistically significant relationships between specific behavioral, demographic, or lifestyle habits and the future onset of dementia? This would be determined by rules left, if it was less than or greater than 1. Second KPI was, can the model produced by this project provide a sufficiently accurate prediction for dementia based on the datasets, which would be determined by the area under the curve score, the false negative rate, sensitivity, and the false positive rate of a classification model. Third, how accurate is it compared to the current models tested in the field for diagnosing dementia? Therefore, I would compare this mostly towards the Cambridge University model that was produced with an 82% accuracy, which was trained purely on cognitive tests and MRI scans. And fourth, are the findings of this project statistically significant enough to warrant further research and analysis using larger and more varied datasets? For the first KPI, yes, I was able to find rules with statistically significant lift as evidence for correlations between behavioral and demographic information with a negative diagnosis for dementia. Few direct correlations were made with a positive diagnosis, though many of the identified correlations coincide with the chi-squares determination of variable of significance in predicting the target variable dementia. For the second KPI, I was able to develop 4 classification models with good performance, achieving an area under the curve value of at least 0.81 in each model. I was able to determine the optimal model for use in a diagnostic setting based on the area under the curve, false negative rate, sensitivity, and false positive rate. In considering these 4 metrics, I determined the random forest model maintained a low false negative rate while also producing the highest area under the curve value, as well as demonstrating a sufficient sensitivity and specificity to clearly distinguish between the negative and positive classes of the target variable. For the third KPI, I'll focus on just the Cambridge University model. Their model was trained on PET and MRI scans and achieved an accuracy of 81.66 with an area under the curve of 0.84. My champion model, which was the random forest model, achieved a 77.6% accuracy but an area under the curve of 0.873. Both models had similar sensitivity, however, the Cambridge University model had a greater specificity. I would, though, point out that the gradient boosting model achieved a greater area under the curve, similar accuracy to the Cambridge model at 79.1%, comparable sensitivity, and a slightly lower specificity. Of course, I would point out that Cambridge University's model was made for actual diagnosis of dementia through pattern recognition of these medical images, while the model produced in this project was merely to create a screening tool to recommend patients who are at higher risk of dementia for regular screening. Therefore, for the third KPI, I would say I was successful in producing a comparable model in terms of accuracy performance to the models currently deployed with less training data available, which leads me to the fourth KPI. The models produced by this project displayed good accuracy and performance in classification, and the association rules and chi-square test were able to show specific demographic features and behavioral habits show significant predictive power in determining a patient's diagnosis for dementia. However, the findings in terms of the association rules mining was somewhat inconclusive due to the lack of rules associated with a positive dementia diagnosis. This was again likely due to the class imbalance of the target variable within the datasets, as well as the smaller sample size available. Therefore, the conclusions made in this analysis that gender, race, sleeping habits, and level of physical activity can affect a patient's development of dementia or risk for development of dementia should be retested to confirm these conclusions and ensure they can be safely used to assist in medical decision making in the future. So, in conclusion, I was able to show demographic traits such as gender, smoking habits, hand dominance, sleep quality, and level of physical activity may affect the development of dementia based on statistically significant correlations. I also showed it was possible to produce a diagnostic screening tool through machine learning methods such as decision trees and ensemble methods with high performance and accuracy to identify patients at high risk of dementia based on information that could be gathered without prior medical testing or imaging. Finally, through the results of association rules mining, chi-square tests, and the models chosen to develop the screening tool for this project, I was able to show the way different features and symptoms contribute to the development of dementia is multifaceted and nonlinear. That this is an area that still requires continuing study to improve public health for our elderly in the coming years. In terms of recommendations for future study, I recommend further study into whether educational level, ethnicity, gender, hand dominance, and sleep habits show significant trends in larger quantities of data. I think the most important thing would be to see if it's possible to replicate and expand on the trends discovered within the two datasets observed in this project to better identify what behaviors or features can be risk factors in developing dementia. If we can improve our understanding of the risk factors for dementia, we can improve our interventions for it, whether it's changing habits for smoking or drinking, or new pathways for our drugs can interact with to better control the symptoms. I also think it's important people in the healthcare industry collect more patient demographic data for analysis, as this could uncover trends based on maybe location or obesity or even economic level with dementia. It could be possible. As for lessons learned in this project, I certainly realized that integrating datasets requires very careful consideration and planning in order to minimize data loss and ensure compatibility when it comes to the units and the scales. In addition to this, I also realized just how important proper notation is when it comes to coding in order to ensure that when troubleshooting is necessary, you can find which section you need to fix rather than searching through all of the code again. Finally, when it comes to choosing the optimal model, when you know which metrics are the priority, it's more important to look at the whole picture instead of just looking at that specific metric. Because even though that metric might be the priority, it may also be painting a very false picture of the performance of the model overall. Here are my references. Thanks for taking the time out to listen to my presentation. I hope you have a good day.